Hello, welcome to everybody. It's nice to see you here. This is the last meeting in our sort of before the summer break. I'm Jonathan Bowen, chair of the BCS FACS. I think I know quite a lot of you already. So we're going to have a break after this talk over the summer, but although there's nothing on the website at the moment, we are going to have meetings from September onwards. We've got some meetings planned for September, October, November and December, and they'll appear on the website before too long once we have some information on them. Anyway, today I'm going to hand over relatively quickly to Keith Lyons, who gave the last FACS talk, and this is a sort of related talk, so that's why he's going to introduce it and introduce you to the speakers. So over to you, Keith.
Okay, thank you, Jonathan. So welcome everyone to this evening's webinar. As I say, this really does follow on from our previous one regarding the National Physical Laboratory. As we were saying, that we are still very, very interested in anything that can really help make better quality software, and particularly things like formal aspects. How we approach a lot of that work these days is through joint appointments and partnerships. And one very key one at the moment is with the University of Strathclyde, where we are working with this evening's speakers, Frederick and Connor, and they will be just giving us a presentation on their work. So before handing over, what I will do is I will give you a brief introduction to Frederick and Connor. So starting with Frederick Norvell Forsberg, he earned his PhD from Swansea University for a foundational theory of data types. He was a postdoctoral researcher in Birmingham and at LMU Munich before joining the mathematically structured programming group at the University of Strathclyde, first as a postdoc and now as a Chancellor's Fellow and Lecturer. And we also have Connor McBride, who's one of the founders of dependently typed programming, which is going to be absolutely key to this evening's talk. And after earning his PhD at the university, he's been a big doctoral researcher at the University of Nottingham, and is now a reader in the mathematically structured programming group at the University of Strathclyde. He's a member of IFIP working groups 2.1 on algorithmic languages and calculi and 2.8 on functional programming. So as I say, they've been doing some really interesting work for us jointly with us. So definitely be looking forward to this evening's talk. And even more exciting, it's going to be a whiteboard talk, not the usual SharePoint. So that's great. So if I just spotlight the video, over to Frederick and Connor.
Thank you very much. Cool. Thank you. You do the do. I'll remove the title slide and start with a kind of teaser where I invite you to spot the error in this Haskell program. Doesn't really matter if you don't know Haskell. You can probably guess what's going on. It's about lists, but not all lists have tails. So it's important to test whether a list has a tail before you compute that. Can anyone see the type error in this program?
I think I can see it. Maybe you could...
Well, hang on a minute. I asked for the type error. All right. The problem with this program is that there is no type error in it. It's a deeply unsafe program, which has no problem getting through Haskell's type checker. Because you can see that I'm exactly performing the tail operation in the situation where it's unsafe to do so, when the list is empty. Any suggestions for how to fix it, possibly from other people in the room?
Well, you could invert the condition, right? Or you could swap the branches.
Just to be on the safe side, I've done both. But you know, the problem here really is that there's some sort of connection between the test that is being done here and what behavior makes sense in the two branches. And the normal typing rule for if then else doesn't take into account, in what way things make sense in the two branches relative to the condition. That's our problem, is that in practice, the correctness of programs and data are very often relative to other data. And type systems that we're familiar with very often impose the approximation that all elements of the same type are considered effectively, for type checking purposes, equal. And there's absolutely no way you can build trustworthy anything on the back of that. So we're on a mission to project more understanding and to make more sense of programs and data. And we're, a large part of that is based on a reversal of the kind of standard issue type system disciplines of the 80s and 90s, where the question is sort of, what is 3? And maybe 3 is an integer or something like that. But there was sort of this idea that there are things and we figure out what their types are. Time goes this way. And our point is that you have a lot more fun and make a lot more sense if you turn around time so that you're checking, does 3 make sense in some situation? Maybe. There are lots of things that could accept 3. 3 might be the number of brain cells that I still have left, or it might be the length of a list, or it might be a number of kilograms. There are all sorts of ways in which the same underlying data might be made sense of. So what we're in the business of doing from 50,000 feet up is figuring out how to make better context-sensitive sense of data as they get used. So instead of expecting the data to be able to tell us what they are, we want to be better at expressing the ways in which we hope the data can be made sense of. So that's our kind of overall mission. I'll leave Fred aboard.
Okay, so let me give you a more concrete example. So Connor was talking about lists at the very beginning. So let me give you the type of lists and how they make sense. Right? So we're saying that if A is a type, then list of A is also a type. Right? So if A makes sense as a type, then list of A makes sense as a type. And now we can describe what lists are by saying how to construct lists. And I'm saying that list of A always accepts the empty list as an element of that list. That's my base case. And I can say that if I have an A followed by some A's, and I'm asking the question, when does list of A accept this?
Your writing is getting smaller and smaller.
Right, I'm trying to make it larger.
Yes.
Well, what do I need to do? Well, I need to check that A accepts the first element, and I have to check that list of A accepts the tail of the list. Right. So notice that, again, the type comes first, and then afterwards, I'm saying, does it make sense to accept this as an element of this type? Okay. So that's how we introduce lists. How can you get things out of lists? Well, we do this by pattern matching. So let's say that I want to take 2 lists and stick them together and make 1 list. So I'll write this as ++, and I'll give its type up front. it takes one list and another list, crucially of the same elements. I'll try to write larger again, and it will produce yet another list of the same element type. Right? And then I do this by saying, okay, what is the empty list appended to something, and what is x comma x's appended to something. So I have to give each of the cases for, I'm choosing to focus on the first list here. Okay, and then one point is that I can now get some help from the type system in order to figure out what I should put here on the right-hand side, right? Because I know, because I've stated my type up front, I know that here I have to produce a list of A's. And I know that I have exactly one list of A's around. Well, I can always make the empty one, but I have one more that I've been given. So it makes sense, probably makes sense to give this one back. Right? And here, well, what should I do? Well, I want to use everything. And I don't want to return the empty list. So I probably should start with something, comma, something. And I have exactly one element around. This would probably be x, comma, something. And then here I have to produce yet another list of A's. And now I have this one, or I could do a recursive call on these ones. And since I want to use everything, I'm going to do a recursive call here. So we see that the type system helped me write the function, but it didn't help me as much as it could have done if I had more information about the lists involved. For example, if I kept track of the length of the lists, then I could see that none of these lists would have been an acceptable answer to fill this hole here. Only this one would work. Okay, is there anything else I should say about this?
Yeah, well, I guess you should think about the equational theory of this operation.
Right, so that's a good point. So some equations we can read off from the board here, right? For example, that you take the empty list and you append it with something else, you get that something else. But what about the equation x's append empty list equals x's? This should intuitively also be true, right? So if I take one list and I append nothing on the other end, then I get the same list back. But this is not one of the equations that I've written down here. So it's not obvious that this equation should be true. You have to prove it. And similarly, so what if I append x's, y's, and z's, but I bracket this one this way, and I bracket the right-hand side the other way? This is also an equation you would expect to hold, right? Because you're just putting things together one after another. But again, it's not obvious that this equation is true just from these two equations. You have to prove something. You want to say something, Connor?
Yeah, I was just going to say that we spent a lot of time working in proof assistance where these equations aren't obvious. Where they are provable, but it's not obvious when to deploy those proofs. So the equational theory of lists that the proof checker understands does not even incorporate absorbing the neutral element on both sides and associativity. And then people try and do category theory in these proof systems in which even the simplest available form of associativity is not a given. So that is kind of a worrying technology failure that we're trying to get over.
I think it's your turn to go.
Yeah. Okay. Yes. So what we actually quite like, and we're in the business of ensuring that we can actually understand that lists are a monoid. I'm going to keep lists here and actually give dependent type. I was talking about 3 earlier, and so what I want to introduce is a kind of candidate alternative type for 3. So I'm going to say that if I'm I'm going to talk about what it is for this thing to be a type. And that's going to be if, so strictly speaking, I should annotate that with an X, but I'll usually stop. If X is a type, little x is 1x, and list of x accepts x's. So this is going to be the type of pointer to a particular element of a list. So straightforwardly, I'm going to say that x, the first element of the list, is pointed to by the number 0, and that if we want to check whether x is pointed to by 1 plus n in y followed by x's, we should check that x is pointed to by n in x's. So the idea here is that some numbers do a very particular job of picking out a position in a list or in an array or something like that. So not all numbers will make sense as the position of an element of a list, but some will. And when you use a number that represents actually a position within some data structure, it's good to give it a type that reflects that extra understanding of the meaning of that number as opposed to some other numbers. It's noticeable that if we take the element type of lists to be the unit type, then list of unit, so that's to say the elements are boring, the only information is how many there are. List of unit is the type of natural numbers, at which point this becomes the type of just picking a position from a finite number of positions. It really is just a type of natural numbers with a given upper bound. So that makes perfect sense as an index into an array. But what we're going to be getting interested in is using less boring lists than the ones that just look like numbers, where it's important to pick out something special about one particular position in a data structure. I think it's Fred to go.
Yeah. So let me give you an example of this, which is something like an array. So let's do the boring case first, but it's not so boring. So I'm going to call these SVEC, so VEC instead of array, and S for simple, or like larger, simple, or maybe if you want, you could read this as sparse, in the sense that you don't have to fill in what's not there, and it's going to take a list of indices and give us a type of vectors. Right.
So you want to do it that way?
Yeah. So maybe I should have written that as a rule. And the definition of SVEC given some list of indices i's says that if I, for every I and for every way I can occur in the list, I have to give some element in some type P of I. So really I should have P as an argument here as well. So, and now you can choose different P's to get different interesting things. So for example, you could, if you want, just take P of I to constantly be, say, the real numbers, if you know what these are. And then you just get an ordinary vector, right? For every element in this list, you get an element. So if you have 5 elements here, then you get 5 different elements. You get a vector with 5 elements. But you could also now have something that actually depends on which element was picked from the list. So you could say that if I have an even number, then I want a positive value. And if I have an odd number, then I get a negative value, something like this.
Yeah, that's a list of numbers.
If it's a list of numbers, yeah. And in the same way, you could also do matrices, right? So you can say that A simple matrix or a sparse matrix is something which is indexed by two lists now, list of I and list of j, and gives me a type. And I say that such a matrix for some p, given a list of i's and a list of j's, is something which for every I and j, if I pick I from i's and I pick j from j's, then I have to give something in p of I, j. So it's just like a vector, except that I now have two different coordinates, right?
Yes. So it's good to remember that these things are really fancy numbers. But well, okay, maybe I'll just do the next bit. So let's have a concrete example, which springs recently to mind as it's been the exam board period. I often find myself manipulating data structures which display a list of students here and display a list of tests here, and a pair of a position in this list and a pair of a position in this list. Well, that's the whole point, is that the rows all pertain to a particular individual student, and the columns all pertain to a particular individual test. And what goes here is pertains to a particular combination of a student and a test. So this is this is a score, but it's not just any score. It's this student's score in this test. So we're now at a position where, so I've just reinvented the spreadsheet in a slightly more typed way, where I'm trying to say what the cells of the spreadsheet have to do with the legends across the top and down the side. We're now able to explain what is being individuated by picking a position. That's the key thing we're doing.
So this is an example that's close to our hearts, but of course, when I work with MPL, they don't work so much with students, they work with physical dimensions, etc. So that's the direction we're now going to take the rest of this talk. So if I clear this off, then maybe you can set up the physical experiment.
Yes, let's do some physics. In just a moment.
Yep.
So I've got a pendulum here, and I want to figure out what the period of this pendulum is. And what do I know? Well, I know that the mass of the bob, you can see it's pretty much 1g. And I measured the length of the string, and it's 25 centimeters. I suppose I should call that a 0.25 meters. And I know that in this particular part of Glasgow, the acceleration due to gravity is pi squared meters per second squared. And I'm going to ask Fred to figure out what the period of this pendulum is.
Okay, so let's see. So I have no idea, and I've forgotten all my formulas from physics. So all I know is that the time it takes for this to go back and forth, well, it has to be some kind of function of these numbers, right? But if I now consider the dimensions of the numbers involved, then I know that this time here, this is a time, and m is some kind of mass, and L is a length, and the gravity is meters per second, so that's length over time squared, right? And since I want to have an equality here in the middle, I know that I have to have the same dimension on both sides of this equal sign. So I can immediately see that this mass here that Connor has clearly wrongly measured anyway, can't possibly play a role in this equation. Right? This must really be some function h of just the length and gravity. And then I see that if I want to get a time on the left, so I need to have a time on the right, well, then I can't afford to have any length occurring, so I need to divide out the length somehow. So I have to do L over G or G over L. And if I do L over G, that's going to cancel the length dimensions, and I'm going to get something here, which at the moment has t squared, right? It's 1 over t squared. So that's not right because I have a t on the left. So I better take the square out of this, I suppose. That's going to cancel out the square. And then I could still be some dimensionless constant here, which I don't know. Let's call it alpha. But that's okay because I can just do an experiment and measure how long it takes to do this. It's about 1 second. And then I can plug in the numbers I know in order to get the alpha out. And if I do that, I believe I get that alpha is going to be 2 pi. And of course, if you're a real scientist, then you would do this 100 times instead of just 1 time. Right?
Yeah, or you can solve a differential equation, it's minus L over G theta. And then the only solution to that is theta is e to the I root L over G times t, which means you go around in circles with. But this is where the 2 pi comes from. It's making this 0 again.
Yeah. So the point that I'm trying to make is that it's really hard to do this, but just looking at the dimensions, you're kind of led to a formula that it has to be. So you get, just like the types can help you write the program, dimensions can help you write the formula. And we saw that I could do this step by step, just like when I write the program. I did this step and I had t squared. That wasn't quite right, so I had to put in a square root in order to remove the square, etc. Right? So there's a lot of similarities between types and dimensions. So it would be great if we could bring these things together.
So that is, to some extent, our mission. The things that are going to be put in the lists are going to be physical dimensions, the things that are individuating components of our vectors and matrices. They're going to be physical dimensions. So we need to think about how to conceive of these physical dimensions. So what do we know about physical dimensions? There are dimensionless things, and we multiply them. So we expect that multiplying by 1 is going to be the identity, and we're expecting that the grouping of multiplication doesn't matter. We're also expecting, maybe I could branch out with a whole other letter, that we can invert things. We know that there are hertzes as well as seconds. So we expect that d inverse times d is 1. What we've got is the theory of a group, and moreover, we're expecting that meter seconds are the same as second meters, or that area doesn't change when you rotate through 90 degrees. So that kind of stuff. So we're expecting it not only to be a group, but to be an abelian group. Is there anything else happening, Fred?
Well, there's one more thing that's particular about this example, right? Which is that we're actually generating all these expressions that we have from some base units or some base dimensions, time, mass, length, etc. So we actually have something which is called a free abelian group on a actually finite, although that doesn't really matter, set X. So what this means is that we have the set X, we have this free abelian group on X, and we can include the set into the group. So the generators are also elements of the group. And if we have any other abelian group B with such an inclusion, then we can extend that function to the free abelian group. So this gives us a way to get functions out of this group. We just have to give the function on the generators, and then we get it for the whole group. And if you want, you could explicitly represent this thing as functions from X into the integers, which intuitively tells you how many of these you have. So you might need to have -1 ones, or you can just have 1 or 2, etc. But these have to be such that they have finite support. So you can only have finitely many non-zero elements. So the x's such that f of x is not 0, this has to be finite. And what this means is that we can now have a normal form for these rings. Every element x can be represented as a finite list of x0 to some exponent, a0, that's what this function tells me, x1, a1, up to xn, an.
Let people see it.
I'm standing in front of it, sorry. Such that all the exponents has to be non-zero, and x0 is smaller than x1, etc. So this only makes sense if we have an order on the x, right? But when we implement these things in a computer, we will have an order on this because things are just terms which are bit strings, so we can order them. And what it means is that if we represent these elements in our computer, then we can always reduce to this normal form and just compare the normal forms rather than trying to be clever with these equations and apply them in the right way to see if things are equal or not. Just reduce the normal form and compare.
Yeah, it's crucial, in fact, that because what's going to happen is that although values in the free abelian group are always going to be concrete lists, our types are often going to contain expressions with free variables in that are talking abstractly about elements of free abelian groups. So it becomes even more important that we teach our type checker to actually internalize this equational theory. And there we can absolutely make use of the fact that upon any syntax, we can secretly, behind the scenes, impose a term ordering. Right. So we've got our notion of dimensions. They live in some free abelian group generated by mass, length, time, and the other ones that that I don't know about because I stopped doing physics at A level. So what about the quantities that have these dimensions that live in our vectors and matrices? What's the algebraic structure which pertains to them? Well, it goes like this. We're interested in not just in distinguishing the dimension of the whatever it happens to be. So we're going to be working in some sort of structure which is indexed over the free abelian group on some set D of dimensions. I'll borrow Fred's notation. We're going to have types, one type of quantities for each possible dimension. So if the numbers are all different types now, how do we do any arithmetic? Well, marvelously, we're in a position to breathe normally. If we want to be able to do multiplication, then we need at least the structure of a semi-ring. But there's a thing we can do to a semi-ring to make it work in this situation. We can say that there has to be a 0 in every dimension, and that addition has to work uniformly, but only within one particular dimension. So you can see, so these are where G here is universally quantified. Here I'm saying every dimension has a 0 and an addition. However, the multiplication structure of the semi-ring is going to be fussier. The multiplication of the semi-ring has to have as its index the one that means dimensionless. Meanwhile, the multiplication of the semi-ring, it doesn't matter what it multiplies, as long as what you want. Maybe I should choose Fred's. Likewise, I should compare those. So that's to say, when you multiply two quantities, you multiply their dimensions. So this structure, which is where the additive stuff is uniform for all dimensions, and the multiplication follows some other multiplication. It's called a semi-ring graded over a monoid. And if you want to do other fancy stuff like inverting matrices and things like that, you will probably need a field graded over a group, where the taking the reciprocal of a quantity is going to invert the dimension that's part of the type. So the deal here is that we are now doing dimension typed arithmetic. And if we've got a graded semi-ring, we should at least be able to get as far as multiplying matrices. I think, is that?
Yeah. Right. So here we can, for example, add two lengths together and we get the length. And if we multiply a length and a time, then we get the length time, right? As we expect. So how do we move from this to matrices and vectors? Let's start with vectors because it's a little bit easier, right? So the first thing you could think to try is to just say, okay, let's just now have a vector full of R of G's for some G, right? So you say a vector full of lengths, but often that's not quite enough because you might want to have different, for example, if you want to take the, you want to have a vector full of partial derivatives, then they're all going to have different dimensions, right? So we don't want to have one vector full of all the same things, the uniform vector. What we actually want to have is that we want to have a vector where if we are given a list of dimensions, so this free reading group over D is our dimension. So we have a list of dimensions that describes the dimension for each element in the vector. Then we're going to get a type of such vectors. And how do we define it? Well, given such a list of G's, then we're going to say that for every index, if I comes from G's, then we get something which has dimension I. So just like before, but we now instantiated our list to be a list of dimensions, and we have instantiated our codomain of this thing to be exactly this graded semi-ring that we had up here.
Right. Okay. So it's hopefully clear. Okay, so There was a question.
Yeah.
Yes.
How does division work? Meters per second. The dimension L divided by T.
Right. So the generators. So that's L multiplied by T inverse. So. And yes, if we are expecting to do division as well, then we need a full-on field graded over a group where the type of the reciprocal also does the inversion in the group. Yes, so that would be takes R of G to R of G inverse. So this is an inverse in the group. This is inverse in the graded field. So it's the usual deal. Well, usual for me. We're using the group to represent the pertinent information about the quantity that we really want to police in its type. We don't have to expose the whole of the information, but it's good to be able to say, actually, there's some pertinent aspects of this data that's important to keep straight. Wouldn't it be great if that was in the type? And we're going to have more of that in just a moment. So the question is, what would be, if we've got some vector like this, right, we can add them. It's clear that adding vectors is going to work pointwise. If I have two such things, if I have x's and if I want to add x's and y's, I don't want to concatenate them, I want to add them, then if I want to say what's at position n, right, so these things, I guess I should give types to them. The point is that this is vec g's and that this is also vec g's. And I'm expecting to get out something in that's also going to be in vec g's. So when I'm saying what happens in position n, the type of this thing is g chosen from g's. So I'm having to say what's going on at the dimension associated with this position. So all I now have to do is project out the quantity in position n, which it lives in Rg, and add it to the thing at position n in the other vector. And what we've done by bothering to single out the dimensions at the positions in the vector is to be able to impose conditions such as that in the same place, in the corresponding places in both vectors, we have quantities we can add. So we're getting some progress there already. And then the next fun question is, if I wanted to take the inner product of two vectors and get a result at some particular dimension, let's suppose I want to take an inner product x's dot y's, and I know that this is a vec g's, and suppose I want this to have type vec, oh, not vec anything, I want this to have type Rg. So if the inner product is supposed to have dimension g, and my first vector has a bunch of possibly different dimensions g's, can we figure out what dimensions we need to put in to make this inner product make sense? And the point here is that we compute the inner product by adding up a bunch of quantities, all of which must have this dimension G, but we compute it by pairwise multiplication of the elements of these two vectors. So we can tell from that that the second vector had better have type map G inverse multiplies G's. So there's now some connection between what's at each position in the first vector and what's at each position in the second vector that enables us to say like when this inner product makes sense. So in particular, what happens if I pick out some I from G's, then I know that I'm also picking out a G inverse I from that thing. I know whenever I do, so that's the point, is that selection from a list is stable with respect to list mapping. If I do a function to all of the elements in a list, all I have to do is the same function to the element that has been selected, and I know the corresponding number makes sense. So I know that if I have one of these, the same, I can turn it into one of these. Correspondingly, when I do the projections, what's going to happen? Shit, what have I done wrong? I've done lots of things wrong. Isn't it great when you can actually see what you're doing wrong? Because what's going wrong is that I want to do multiplication by G after inversion. Right. Oops. Which gives me exactly the inverse on my I instead. So here, when I multiply, when I've picked out an I from here and a GI inverse from here, and I multiply them, I get exactly a G. So the point is, yeah, we can now express these structural conditions that ensure the operations we're going to do match up. But it's absolutely mission critical that the type checker can muster enough group theory to see why these things match up, to see why I times G times I inverse is G in an abelian group. If the type checker can't just see that, then we've got a lot of theorem proving to do. Fortunately, thanks to Fred's normalization technology, the type checker can just count the i's and see this I cancels that I inverse, leaving us just the G that we're looking for.
Okay, let's try to take it one step further. And instead of just considering vectors, let's also consider matrices again. So I want matrices where every entry in the matrix has an appropriate dimension. And the first thing you could think to do after you ruled out uniform matrices, because they're kind of boring, right? You could think that now, just like I had my vector indexed by a whole list of dimensions, I have to have my matrix indexed by a whole matrix of dimensions, right? But it turns out that this is the wrong thing to do, because these matrices aren't closed under multiplication. So the next thing you try to do is you try to emulate what we did before, right? And you say that a matrix is indexed by one list of dimensions.
I think you just write dim for dimension instead of frag D. Yes.
So this will be the dimensions of the rows. And then you could say that I want to have another list of dimensions, which will be the dimension for the columns. And then I will get one dimension here by multiplying the row and the column, right? And if I do this, I get the type. But the problem with this setup is that it's not unique again. So we gained a lot of mileage out of having these unique normal forms for the abelian groups, right? Because that meant we could just reduce it and compare on the nose. But if I have the dimensions like this, then I can always take one multiple from the column and move it to the rows instead. Right? So there's no unique types anymore. So what is better is to take this common thing and put it in the top left corner here. So we have one dimension of the top left corner. So these are the rows.
That should be a dim.
This would be a dim, yeah. This is the top left corner. And these are the columns. So for every position here, I get it by multiplying the, let me just write it. So the matrices, I have A's, B, and C's. So these are my A's. These are my B's. Sorry, this is my B. These are my C's. Well, this should be, again, we have to choose two indices, and we have to pick I from the rows. And we have to pick J from the columns. And we have to give back some dimension thing.
You need to remember the B's.
Uh,
Yeah, so you're
just one
picking,
B.
yeah.
And now I give back I times B times J.
Yeah, no, you need some ones on the
Right. So
C's.
now I get too many B's. So I'm going to only pick something here when I'm not in the first row or the first column. So
Let's see, point.
sorry. So it's a 1 for the first column, and then an ace. J is a 1, and then a C's. So in this column, I'm just, well, let's do an example. So let's say that I have a 2 by 2 matrix. Then I have dimension B here in the top left corner. And, well, let's do a 3 by 3 maybe.
Why don't do it concretely?
Right.
Yeah.
Okay, so I have time, that's my B. Right, so Ace is mass and time inverse. B is time, and C's is length and time. Then what I get, top left corner is time. Here I take M times B. Here I take T inverse times T, so that's just unit. Here I get L times T. And here I get T times T, which is T squared. And here in the middle, I do M B L and M B T. And here it's T inverse T, so that cancels. And I just get an L. And I get the T inverse T, T. So we get the T. Right, and there's one final complication, which is that it's advantageous if instead of having A's here, we take the inverse of all the A's. So I'll just put an inverse in here. Because Connor will show you why when we do multiplication in a second now. So that's going to just invert these things.
In a few more places, I think we have to. Right, so we've got our type of matrices, and it's very much has the sort of flavor of that inner product calculation I showed you. So what if we have, if we want to explain which matrices we can multiply, well, then we might have, I'll just draw some pictures This one has this many rows. This one has that many columns. So we're going to be computing what's this? That's the thing that goes here. The thing that goes here is going to be the inner product of a row and a column. So this has to have a suitable dimension. And so here, this is B, A's, C's. And we should figure out, maybe this, I'll make this thing is going to be, I'm going to have some D's down the side here. This is going to be an E. And these are going to be some F's. Then what happens when we pick, what do? We pick we pick a row, we pick a column. So we're going to pick the same position in the C's and the D's. And we're going to multiply. So we're going to choose some A from A's. We're going to choose some F from F's. And then what are we going to do? We're going to choose, so that's picking which row. Then for a typical for each C and D in the corresponding position, I'll fix this up in a moment. We need to compute, well, something, sorry, I should, no, that's fine. I'm going to get something which lives in A inverse times B times C times D inverse times E times F. That's going to be when I'm at position, when I'm picking a C from the C's and a D from the D's and multiplying. I'm going to get something with these dimensions. And I want to get something which has, whose dimension is A inverse, something consistent, F. That's it. The dimension that goes here, you know, these are, I'm going to have the same A's here and the same F's here. And I want to pick something, some mystery G that goes there. So how do I make sure that there's some constant G that always works out here? I make sure that whenever I'm picking C from C's and D from D's, that D inverse is always the same as C's. And it's always the same as C. I make sure that these cancel. And what do I do to achieve that? I actually say, you don't get to choose D's freely. This has to be C's as well. So now we really are just picking a single C from the list, a single dimension that makes sense as a column in one vector and a row in the other. And when we perform that unification, we see that we have C and C inverse cancelling in the middle, leaving us with G given by B, E. So this is B multiplied by E. So what's going on? in terms of the top left corners, we're just multiplying dimensions. In terms of what's going down the rows, that's being copied from the first matrix to the output. In terms of what's going on with the columns, we're copying that information from the second matrix to the output. Meanwhile, for the internal dimensions, where previously it was just the sizes that had to match, now it's the dimensions that have to match and cancel with each other. So what we've, once again, the slogan of this talk is numbers are boring lists, and wouldn't it be good to have interesting lists? So what we're doing here is, instead of saying we're just going to talk about sizes of matrices, which are numbers that ought to match up, we are moving from boring lists to interesting lists, lists of dimensions which can cancel when they appropriately match up, and that gets us some useful matrix operations.
So let me just write down the type of that explicitly. So we have that multiplication takes a matrix A's, B, C's, and a matrix C's, D. Did we go down here? F's?
Sorry, C's, E, F's. Yeah, is what I had in my picture. Yeah. Editing. Yeah, sorry, spoiling your fun. I just wanted to match the picture.
Yeah, right. So that's me. Right. So you see that this has to exactly match this. Right. Just like normally, you can only multiply an n times m matrix or an m times k matrix, right? It's the same thing, but now all of the dimensions have to match up. What about the identity matrix? Well, for the identity matrix, we want to have ones down the middle and then zeros everywhere else, right? And if you remember, we had that 0 was a quantity in every dimension, so that's fine. There's no problem to put the 0 wherever you want, but 1 only made sense over the unit, right? So we have to make sure that for the type of identity matrix, we have to have units here along the diagonal, right? And one way to do that is if we make things cancel out again, just like we did down here, right? So if I have the matrix A's, B, A's, then what will happen at position ij? Well, I will have an I. So at ij, I will in general have I times B times I inverse times B times j. But if I'm on the diagonal, then I equals j, and then this I inverse and this j will cancel out, right? Right, and then I get the B left, so that was wrong. This would just be a 1, so that I get an R of 1. So we see that the identity matrix makes sense at this type, which you could, if you want, call a kind of generalized square matrix. Right? So it's not only square in size, and that is n times n, but it's also square in dimension. You have the same dimension along the rows, except inverted, as in the columns. Right? And the same thing happens if you try to do things like determinants or traces. This is usually the interesting notion of a square matrix. Just having a square size is not enough, because that's not taking the dimensions into account. But I think we'll skip that now and move on to the summary.
Yes, I think we're pretty much there at if the identity and multiplication makes sense, we're getting somewhere, and you do. And there's plenty more. I should also say that there's a chap called Hart who figured out all of this stuff, and what we're figuring out how to do is to steal those ideas and turn it into a type system for programs, it essentially scale up Andrew Kennedy's work on dimension type inference to data structures which have kind of interesting spatial relationships between which dimensions need to be where in sort of tensor-like structures. So I guess what are the messages that you can take away from this? One key message is that sizes are numbers, and numbers are just boring lists. And you can very much use lists to describe what's going on in some spatial structure by saying what key salient kind of individuation is necessary in each of the different positions within this data structure. And I guess the next message is what I said earlier, which is that we should use we should think of types like this one, that I is chosen from this list, as really being just types of numbers, but numbers that have been given a local significance. And then finally, I guess I'll say that if you want to build a practical type system out of these observations, these algebraic observations, the type checker needs to be able to do enough algebra. So the equational theory between types that the type checker has to decide needs to be able to do enough group theory, for example, to see that this cancellation happens. But we're getting there.
Yeah, and here we were lucky that they were just next to each other, right? But in general, you need to really use the whole theory. So we need these normalization procedures in the implementation to make any sense of it.
Yeah. So that's really what's happening, is a move beyond mere symbolic evaluation during type checking, which we've spent since the 1970s getting to nearly now. Our approach to symbolic evaluation during proof checking or type checking has pretty much been, even though there are free variables around, run programs the same way you would run them at runtime. And when you trip over a free variable, you just get stuck. And we're basically saying, nope, we got to do better than thinking about how to do symbolic evaluation, just copying the way we run things at runtime. But the symbolic evaluation that we do in the course of checking equality between types is a whole other game than just normal program execution. And in particular, it's really good to do that in a maximally type-aware way. This is a notion of execution where if you erase types before you execute programs, you've had it. Right. So it's keep the types around and do as much algebra as possible. And then you can actually exploit lovely algebra like the stuff Hart figured out for dimension matrices. So we stop there?
I think we should.
Okay, thanks very much. Can you hear me?
Yeah.
Well, thank you so much, Frederick and Connor. Really do appreciate this. I certainly know when I asked you to do this presentation, I wasn't expecting a real proper old school whiteboard presentation with actual 3D physics demonstrations. So that is absolutely marvelous. Thank you so much. It's great, appreciate it. And I should add, what a pleasure it's been working with you guys during this joint appointment. And hopefully we're going to be able to take this one forward because it's great. We've had a few comments come through on the chat. Can I take co-host privilege first and ask you a question that, I don't know, might seem a little naive, and I probably know what the answer is, but let's find out anyway. I mean, we're going to take all this wonderful theory and we're going to actually start applying it and using it. Would you say that functional languages like Idris, for example, are really the only option for taking this kind of theory forward into practical applications?
I don't actually think so. Although, I always enjoy trying to be kind of a bit gateway about this sort of thing. I love it when people decide that they want to pick up language like Idris as a bit of a hobby, but realistically, we cannot achieve world domination by conquest. We need to achieve world domination by infection.
Yeah.
And correspondingly, what we absolutely must do is come and get you where you are. You know, so the approach that actually, again, it's that man Andrew Kennedy again at Facebook is operating a very, very crafty frog boiling program on not merely the Facebook code base, but the Facebook employee base by adding, essentially by creating this language hack that has this this optional extra type system for PHP.
Oh, really? That's interesting.
And basically, types are like fancy formal comments where you try and say a bit more about what sense you hope your rat's nest of untyped programs are making. And the type checker isn't going to stop you doing anything, but it is occasionally going to say, I can't really see why this bit of your code makes any sense, and I'm sure you're right. Go on if you want. And then what they do as a social process, especially as they have a closed code base that they can just search for type system violations, is that they make certain kinds of warnings from the type checker as socially stigmatized gradually, but it takes them a long time to say anything is actually forbidden. So what's important here is having enough language to write down the kind of sense you're trying to make in your program. And there's not any particularly good reason to believe why that having such a language in which you explain the sense you're trying to make is only for hardcore next generation functional programming language.
Yeah.
I think absolutely. Actually, never mind PHP. I want to do this for Excel.
Well, don't we all? Wouldn't that solve so much if you could? Or VBA even. How about VBA? It's wonderful. So I'm just scrolling through, looking at some of the comments. We've got one here from Jeremy. I don't know if we can unmute people, Jonathan. It came in during the talk, actually. Yeah. It was how a bad
anyone can unmute.
Wonderful. So if we can unmute Jeremy, perhaps. How are bad operations ruled out?
Or was it which bad operations are ruled out, or how are bad?
Yeah, which bad operations are ruled out? I beg your pardon. Which bad operations?
Yeah. Well, so basically, I try to think of. The trouble is, it's so difficult to think like a sinner. Sometimes, just kind of sort of stupidly ill-conceived that more or less any operation that computes the period of a pendulum that actually non-trivially uses the mass of the bob is just a type error now. But similarly, so one thing's for sure, we're enforcing all of the size invariants, let alone, essentially we're just doing fancy size now. It's what needs to be in what position. So indeed, there are internal invariants, even to write down a matrix. But if you're just shoving data into a matrix in the first place, then for that to be a reasonable matrix, you've got structural constraints happening there. So for example, I don't know, if you're building a matrix by starting with some measurements and then kind of each row is the next derivative with respect to times, then that's going to be fine. But if you mix up which rows a particular derivative calculation goes into, then that's going to be an error.
I think it's also good to not only think about avoiding bad things, but actually enabling good things, right?
Yeah, that's
you really use this type of information to write the program you want to write, and and the type checker will help you do the right thing. So for example, if you try to do Gaussian elimination, and you try to write down the elementary row operations, you can implement these and you give them types, and then when you apply them in the right order, then you can use the type information to see which one of these actually makes sense as the next step. It's not just about being told off when we do something wrong.
Yes, that's the thing about 20th century types tell you off. 21st century
So should
tell you what the program is. Or at least they very tightly structure the search space for what might possibly be reasonable as a program. Which means basically floundering around in text editors becomes an extremely bad strategy for producing well-typed programs, and we should just stop.
I can't think how anyone would disagree with that.
Yeah, you know.
So we've got one coming from Uma. I don't know if you answered this one. You might have done. The ID matrix is not necessarily unique, right?
Right. I did answer this, but I could also answer this live. So it's not unique in the sense that you have one for every list of dimensions here, right? But just in the same way that you have one identity matrix for every size, if you're not keeping track of the dimensions. So it's unique, but you have to keep the sizes of things and take these into account.
Okay, thank you. So we have another one here from Anton, highly relevant. Could you deal with different units, such as metrics versus imperial units, which cause the Ariane crash, or different money units? I mean, this is really the whole point of the exercise, is it not?
Classic. It's important to distinguish between a unit and a dimension.
Yes.
If you want to represent any of these quantities by numbers, then you need to pick standard units. But here's a tip. If you want to exchange numbers as opposed to quantities, then it's important, like if you want to print them out, it's important to print only dimensionless quantities that are actually numbers, so that the question which is answered by printing is, what is this mass? You need to, in order to get something dimensionless, you need to divide by a unit, right? A unit is a standard dimensioned quantity. So numbers, right? How many kilograms a mass is a number. A mass is not a number.
Right, I'm picking the wrong example.
Yeah. Okay. How many meters a length is a number. A length is not a number.
But if you have a constant meter, then you can always divide by meters to get something unitless, right?
Yes. So, but the marvelous thing about this is that if you actually treat these types as being abstract quantities that you can only relate to numbers in the presence of units, then you can perfectly well add feet to meters and demand an answer in cubits and get the right answer. Because whatever standardization is being done behind the scenes is representing, is doing the right thing to ensure that any kind of numerical representation is fungible by the operations. Right? Whatever is actually doing addition for quantities is going to have to choose units to turn them back into numbers that can be added by the hardware.
It's only a problem when you escape into another type which doesn't keep track of their dimensions. Right?
As you say, the fundamental thing that undermines it all is the dimensions. It's the beginning point. You choose your dimensions and then you're worrying about your units and things like that.
Yeah, but the ideal situation is where they could have made the same mistake. McDonnell Douglas should have been perfectly free to work in imperial units, combining their code with NASA using SI units. But they should have been working with types for quantities, not types for numbers. And then the linker would have sorted it out. Right. That's the whole point, is
or if
that need not be a mistake.
Or if you insist on conversing in strings, then doing it this way, you can keep track. I mean, you're trying to print something of dimension length, and it's not allowed by the type. And then you realize, oh, I have to divide by my unit in order to fix it.
Okay, we've got quite a long question coming from Tim. Jonathan, can we unmute Tim Devonier? Perhaps you can ask it in person, Tim.
Yes, here I am, unmuted and visible, I think. Okay.
Hi, loud and clear.
Go ahead, Tim.
Do you want me to read my question out?
I think so.
Right. Everything you talked about is specialized to physics, and there are aspects of physics you haven't covered, which perhaps you've done behind the scenes, density force and so on. But my question is, don't you need to expand it to cater for things like, or potentially cater for things like mechanics, fluid dynamics, aerodynamics, dynamics, chemistry, biochemistry, brewing, agriculture, you name it. Having explained your particular case, the real step forward to take surely is to make a generic system in which some pioneer in one of these specialized disciplines can lay down basic rules along the sort of lines you've provided. For example, aerodynamics, and then top degree specialists in that can refine it to whatever sub-disciplines exist, so that second degree users can actually check the correctness of their programs in that sub-discipline. You can't possibly cater for all these application areas yourselves, but they exist, and people are writing software in all these areas. So a generic approach must surely be the way forward you might want to go. What do you think?
That's I think that's quite right. We're certainly in the situation where we're only just beginning to learn to teach type checkers particular algebraic theories. For years, for decades, we've been able to teach proof checkers to recognize that we have done appropriate derivations in theories that are defined by users. But the trick here is to automate as much of the algebra as possible. So then the question is, what's the good way to arrive in a domain and set up the appropriate algebraic structures that manage a better sift of sensible calculations from silly ones? And an awful lot of the time, that isn't that, physical dimensions are going to have to play an important role in all of the domains that you've mentioned, but there will be plenty of other stuff, including actually paying attention not just to the physical dimensions of the quantities, but to what entities in the world those quantities are about. So some calculations involving, I don't know, adding my mass to Fred's mass makes sense if we're computing average masses of people in this room, or if we're getting into a lift, the total might be interesting. But there will be other situations in which it's clearly a mistake to sort of mix up data that relate the different individuals. I guess it depends. If you want to do a calculation that's something about my physical state of being, then where my weight might be extremely relevant. Then a calculation which includes Fred's weight is probably dumb. So there's a whole bunch of other kind of local considerations to start getting interested in, and we surely will become interested in these things over time. As we say, where I come from, Rome wasn't burnt in a day.
Yes, I mean, it seems that this is it shows that the borderline between syntax and semantics is actually rather blurred, because there's quite a lot that you can check if you know the context before you actually do any execution. But most language compilers and that sort of thing actually leave most of this to execution time. And of course, there are advantages to checking a lot of this more detailed stuff at compile time, so that people don't sort of go in, or it saves time and effort and all that.
So we are relentlessly pragmatic about this. You know, we want to put the controls for kind of how much of this to internalize in type systems very much in the hands of system designers, rather than be too ideological about it as a language designer, because there are very cheap low-hanging fruit.
Very cheap, sorry.
Low-hanging fruit.
Oh, all right, yes, yes.
Things which have very little effort to do way better than we're currently doing. But you know, we shouldn't, you know, get our kind of type theory pitchforks out and make people model stuff that is just way too complicated to cope with.
I was thinking about these sort of approaches many years ago. As you can see, I'm fairly ancient, so I was thinking about decades ago, really. I came to the conclusion it was rather too complicated to carry on with, but I mean, I think you've made some sort of progress, so that's very good.
Right. You know, so the key thing is it's going to think about it in terms of you've got some data that are going to be manipulated by a computer, and one thing that's interesting to consider is what projection on that data might be useful for the static management of the data. And there are two obvious bad options, namely the forgetful map to the unit type that says none of this is interesting statically, and the identity function, which says you must pay attention to every detail of all of the data and specify exactly what would be right. Yes. So the key thing to vary is the codomain of the projection that is saying what's the statically interesting information about this runtime data. And what we're really in the business of we're building type systems which invert just that projection. So it comes down to which projections are easy to invert and worth inverting.
Yeah.
And that is we recognize absolutely that's a very pragmatic thing. And what we want to give people is the power to choose that to their own advantage.
I would also say that you really need to make use of the computer when you do this, right? You don't submit a batch program and hope that it works. It really needs to be a conversation with the computer and get some help.
Yes.
And that's maybe what's different now compared to 20 years ago.
There are programs I just wouldn't dare write without the kind of support I get from type checkers these days. And more crucially, there are invariants that allow efficient algorithms to be implemented that I would not go near unless my hand was being held enforcing that invariant. Right. So, you know, how often in the past have we tried to do the clever invariant, screwed up, retreated to something easier? That's, you know, in Tony Hoare's phrase, you know, retreat to something which has obviously no mistakes rather than something which has no obvious mistakes. Yes. So in terms of the amount of gnarly invariant that we can engage with without being scared of screwing it up, that's going up several notches. And it hasn't yet cashed out as code that goes super fast, because the people in this sort of business spend more time writing type checkers than they spend writing compilers, but sooner or later that will change.
Mhm.
Okay, so if I could just jump in here, perhaps a final thought from Margaret. So when working in viruses and vaccines is currently important, more important than ever, but it's massively important generally, isn't it? But arguably more important than ever. And this could be one of Tim's examples. That's an interesting point to end the formal part of the evening, I think. So Jonathan, could you just unmute everyone so we can thank Frederick and Con again and just show our appreciation for that wonderful
do
talk?
unmute yourselves. I think I can't unmute everyone automatically. If you wish to clap, thank you very
If we
much.
just unmute ourselves and just show our appreciation for this excellent talk. Okay, thank you.